Hello everyone.
Good morning, sir.
Good morning. So, hope everything is going well after Diwali. And do you have any questions? Okay, so I think today is a Monday. So Wednesday, we will send the copies of your quiz as well as the marks, final marks of your minor as well as quiz marks. Okay, something like PMT. Uh, yeah, for my part it is done, and Professor Sasangdeep is taking some time. He told he need one more day, okay, to finalize all the I think the recopy checking of minor, okay, and quiz also. Okay, and our exam is on 22nd. I saw yesterday, 22nd November, Monday. So exactly 2 weeks, right? Time I forgot. And yeah, how many of you are in the hostel in campus right now? Oh, okay, 2, 3. Okay, but okay, okay, it doesn't make much sense. Why? Because only 20 people, 29 people are here, right? One third, not one third, out of 140 or 135. So anyway, so rest you are in home. So now they are giving a policy, right? That who are onboarded, we need to conduct the on-site exam in lectural complex. So let's see. So do you have any questions from the last class or anything before I start? So we discussed basically the four mechanism, not mechanism, four experiments that you can conduct, and researcher use those three experiments or methods regularly to study the mechanism, okay, of any reaction. It doesn't matter it is an organic reaction or gas phase reactions or any molecular activations, any kind of reactions. These four techniques are widely used to know what is the rate determining step, what is going on, what is the nature of the transition state, what is the possible reaction pathway, the mechanism, okay. So rate law and the rate constant is the basis of all the experiments, and then activation parameters, and then isotope effects and Hammett plot. I hope it is now clear. We discussed a little more details. What is the origin of the isotope effects, Hammett plots, right? Also the activation parameters, how it is determined by Eyring plot, okay, and the significance of those, the outcome of those experiments, and how it will help to understand the nature of the rate determining step. All right. So next, I am going to discuss today uh, about acid and base catalyst reactions that you already know from your Sasangdev's course lectures, right? Am I correct? So he taught, right? Specific acid catalyst reaction, specific base catalyst reaction. Am I correct?
Yes, sir.
Yes. Okay. So I will go quick today. So the reason why I'm telling you again, it is a kind of recapitulations, but I will discuss with examples, okay? And what kind of experiments we will do to establish or to propose the mechanism of a specific acid catalyst reaction or specific base catalyst reactions or GNL acid catalyst reactions or GNL base catalyst reactions that you all know. You know all the derivations, all the plots, but I will just give you highlights, okay? That how these four different techniques, whatever we taught, okay, in last 1 month will help you to understand the nature of the transition state in the rate determining step, okay. So first is the specific acid catalyzed reactions, right? Specific acid. That acid means this is the H plus, okay. So this acid catalyzed reactions is specific with H plus. So in the specific acid catalyzed reactions, you know that the first step is basically, suppose this is an example of specific acid catalyzed reaction, that is the acid catalyzed hydrolysis of ethyl acetate that I am showing again, and this example I am showing again and again, right? For every part of my lecture I am showing couple of reactions. One is the SN1 SN2 reaction type of reactions, another one is that acid catalyzed hydrolysis of ethyl acetate, because this is the experiment in the part of the syllabus of CMP 100. Okay, so this is acid catalyzed hydrolysis of ethyl acetate, and this is an example of specific acid catalyzed reaction. So this is the specific to H plus proton. Okay, so you know from Shashank Dev's lecture that the first step is the reversible protonation. This is the simple protonation of the the carbonyl oxygen of the ketone, okay, of the ethyl acetate. So this is a fast, so the first reversible process. This is a simple protonations to the carbonyl oxygen, right? And then, so what the catalyst does here? So the H plus bind to the carbonyl oxygen, right? And now the oxygen is the OH is the positive charge. It increases the electrophilicity of the carbonyl carbon. This is the carbonyl carbon, this arrow. This is the, let me give a little different color. So this is the carbonyl carbon here, right? Oh, this is the carbonyl carbon. So the H plus, the proton, it binds with the carbonyl oxygen and increases the electrophilicity of the carbonyl carbon, and it helps the attack of water, because this is the hydrolysis. So water will cleave the ethoxy groups to give the hydrolysis product, that is the acetic acid, if R is CH3, right? So the second step is the rate determining step, where the water is attacking to the carbonyl carbon and giving a tetrahedral intermediate. Okay. Then the rest of the process is giving the product. So it's a multi-step process. We are missing another 2 steps, so that you draw. Okay. So in the exams, if I ask you to draw the mechanism for the specific acid catalyst hydrolysis, you need to show each and every step, which is very easy. You can practice yourselves. Okay, it is not like that you will give a step jump from this step to this steps. This is the product. If you do that, you will lose marks. Okay, am I clear? So this is a step jump process here. Okay, so you find it. This is very simple. Okay, that what are the steps we are missing? So if I ask you to show each and every steps in a mechanism, okay, based on this data, suppose I am giving some data which indicates the specific acid catalyst reactions. So I may ask you draw the mechanism. Okay, and mostly whatever the questions I give in the exam, the examples are already in the slide. Okay, or it is similar. Instead of R, I can give it like propyl groups or isopropyl groups. Okay, so if it is the R is CH3, then this is the ethyl acetate, right? I may give R is the suppose isopropyl groups. Same mechanism, or it is a phenyl, same mechanism. Okay, I can give some data which is indicates this is a specific acid catalyst reactions. So draw the mechanism. So you need to show each and every pathway, every step clearly. If you do a step jump, you will lose marks. Okay, so practice. I'm telling you many things. It is not in the slide. Very simple things. Okay, like in a quiz. The first questions 2 marks. Give the definition of a mechanism, right? I told the definition of a mechanism in a very simple way, right? In the lecture. It is not in the slide. Many of you did right. Many of you did wrong actually. Many of you got 10 out of 10 in my part. Okay, and many people also got below 5. Many people got 10 out of 10. Those are very simple questions. Why will lose 2 marks for not telling the proper definition of a mechanism? because many of you didn't listen the lectures, or maybe 30 people are signed up and then many people left, and I don't know what are the another 110 people. Anyway, that's up to you. Clear? Okay, so here you can see in the specific acid catalyzed reactions that you know from the Sosandev's lecture, that the first step is the reversible protonation followed by the redetermining step. Okay, so this is another one example of a specific acid catalyzed reactions, that is the conversion of quinone to quinol. Okay, is a kind of quinol kind of things. Okay, so you can tell this is the alpha beta unsaturated ketone, this one. Okay, and if you treat in acid water, then it converts to the aromatic compound, that is the phenol derivative. Is a phenol derivative. I don't know why some peaks appeared in the left hand side when I give it. I don't know. It happening every class. But anyway, okay. So what is the mechanism? This is an example of specific acid catalyzed reaction. Okay. You may ask questions that how do you know that it is a specific acid catalyzed reactions? So I'm coming next. So what kind of experiment you will do to study the mechanism? So I'm giving the answer. So this is a specific acid catalytic reactions based on the experimental results. So if it is that, so what is the first step? First step will be the reversible protonation of the carbonyl oxygen, right? So it will give the OH plus, okay, and it is increasing the electrophilicity of the carbonyl carbon here, right? And then the rearrangement will take place, the rearrangement reactions, okay. Then 1-2 migrations will take place. You can see the mechanism here. Everything is drawing here, okay. And this is the rate determining step. The second step, the rate determining step. So in a specific acid catalyzed reactions, always the rate determining step is followed by the protonation of H plus is followed by rate determining step. The first step is the reversible protonation, then the rate determining step. Okay, so here rate determining step is the 1-2 migration of or 1-2 shift of the methyl groups. This is a rearrangement. Okay, and protonation is always reversible because it's a fast. It can come out, it can attach, and it can also detach. It's a reversible process. And if it is a fast reversible, means your barrier is less, right? It's a reversible process. So you have the less barrier. So it can go, the starting material and product in that step can go and forth. So your barrier is less. Okay. So your highest barrier will be on the next step, at least not the first step, right? That is the things. And if barrier is the highest, then that is the called rate determining step. All right. So let's skip this. So okay, so there is another one example. So let's discuss more example. Do you have any questions? Any questions? If it is not, then this is the another one example. This is the specific acid catalyzed ring opening epoxide, ring opening of epoxide to gives the product which contains the methoxy and another one alcohol. Okay, so this is a kind of the protected dialcohol product. So this is the ring opening reactions of epoxide, and this is catalyzed by acid. So what catalyst does? Again, the catalyst lower down the activation energy, right, by increasing the electrophilicity of the carbonyl carbon, number one, or okay, here the same thing. So here for ring opening opening of epoxide, the first step is the protonation of H plus, protonation of epoxy oxygen with H plus, okay, to give the OH plus, which increases the electrophilicity of the adjacent carbon. Here is no carbon, carbonyl carbon, so it is increasing the electrophilicity of the adjacent carbon. Okay, then methoxy attack here. So methoxy can attack on the left hand carbon or it can attack on the right hand carbon. Depending on the attack, it will give a different product, right? Okay. So here it is showing that the methoxy is attacking to the tertiary carbon, right? Where the R is attack. So you should think about that why. There is a reason. Okay, this is a fact that you are getting this product. Okay, so the second step is the rate determining step, that is a slow step, and ring opens to give this intermediate. Then the catalyst regenerations, because catalysts need to be regenerated, right? I don't know why my slides it is showing like this always this time today. So a catalyst will be regenerated. Okay, so H plus will leave protonate from the intermediate products and give the final product. Okay, so we have discussed 3 examples of specific acid catalyst reaction. All right, any questions? Any questions? Questions?
No, sir.
Okay. So you know in this slide the content that you have learned in Shashank's lecture, that what will be the equations. Okay, so if you want to so suppose this is a specific acid catalyzed reaction, so you can make an equations which will help you to design any experiments. Okay, the first is the rate equation and you have to determine the rate law. So this is the substrate and H plus. I think Professor Sandeep already taught these stuffs, right? So as I told, I will not discuss much about the equations or derivations. So these are very simple things. So H plus is a reversible process. The protonation is a reversible process, right? Is a similar kind of enzymatic kinetics. That first step is the reversible process, right? To give the SH plus, and the second step is the rate determining step. SH plus is giving the product. Right, so what will be the rate law? So rate is equal to K2 into SH plus, that is the intermediate, and this is a reversible step. So you can easily tell the rate constant, equilibrium constant, that is the second step of equilibrium constant, K is equal to SH plus divided by concentration of S divided by concentration of H plus. Right, it is very simple. You know that, you are expert now for all kind of derivations. So the rate is changes of concentrations of product with respect to time equal to K2 SH plus, and SH plus equal to K into, there is the equilibrium constant. So the first one is the rate constant, second one is the capital K equilibrium constant into concentration of substrate into concentration of H plus. Okay. And now if you can see the first, this is the constant, this is the constant, right? So if you just combine this one, so you can tell this is the K ops, okay, or it is a KSH plus, okay, KSH plus into concentration of S and concentration of H plus. So your rate, I don't know, disturbing so much here, but anyway, so the rate is dependent on the concentration of substrate and concentration of H plus. Let's say it is specific acid. It's a concentration of proton H plus. That means the rate is dependent on pH, right? Its rate is dependent on the pH. So if you do an experiment where this K constant is a constant, and if you do the rate equations at a constant substrate concentrations, then you will see that the rate is dependent on pH. If you do a multiple experiment where your substrate concentration is fixed, then definitely your rate is solely dependent on the pH. So if you plot a log K ops means this one, that is the K into whatever I circled here with concentration of substrate, then you will see the rate constant is pH dependent. If you increase the pH, I think you know from your Sasandev's lecture, right? If you increase the pH, your concentration of H plus will decrease, right? So your rate will decrease. You have negative slope. Am I correct? It's very simple, right? So how do you know this is a specific acid or not? Basically, you need to determine that whether the rate constant is pH dependent or not, right? If it is dependent on pH, if it is the rate constant log of K ops is decreasing linearly on increasing with pH, that means this is the specific acid catalyst reactions. It is dependent on the concentration of H plus. Simultaneously, if you do the same experiment, multiple experiments in a buffer where you can vary an acid part, suppose this is a weak acid, it is a buffer where if you change any acid, suppose it's a weak acid, if you increase it or decrease it, keeping the pH same, because if it is a buffer solution, then you will see that your rate constant is independent on pH. In a buffer, your pH is remain same, right? Even if you add little bit of acid or if you change a little bit of concentration of acid. On those cases, since it is a specific acid catalyst reactions, your rate constant will be independent or remain same on addition of little bit of acid or base in a buffer solution because pH is remain same. Since specific acid catalyst reactions, you will see your rate constant will be much higher in lower pH because here H plus concentration is much higher than higher pH. So you should expect that your rate constant value will be higher in lower pH because of the higher H plus concentration than higher pH. Okay. No derivation, nothing. Only you can understand that what kind of experiment you need to design any experiments to determine whether it is a specific acid catalyzed or not. Okay. So,
Sir?
yeah, hello. Yeah.
So in the previous slide where the equations were given.
Yeah. This one?
This one, sir, yes. So
Yeah.
in this one, can you explain the meaning of the sentence in yellow, the highlighted sentence?
This one?
Yes, sir.
Yeah, the concentration of any acids that might ionize to produce H plus do not appear in the rate equation. Okay. Okay, because proton has the fully transferred to the substrate before the rate determining step. Suppose you are giving, okay, suppose this is H plus, right? From where you will get H plus? You are doing an experiment. So what is the source of H plus? What is the source of H plus? Acid, right? What kind of acid you will use?
Strong acids.
For example, I need example.
HCl.
Okay, HCl, right? Nitric acid, HCl, right? So you are adding HCl, right? You have a bottle of HCl. You cannot have a bottle of H plus, right? You have a bottle of HCl actually, right? Am I correct? It's HCl.
Yes.
Hey, this is a molecule, right? HCl is ionic molecule. In water, it is hydrolyzing, right? It is in water, it is hydrolyzing. Oh, my okay, forget about the left hand pick. In water, it is giving H plus and Cl minus, right? And Cl minus. Am I correct? So this is telling that concentration of H plus, it doesn't matter how much HCl you are adding. Okay. So dissociation of HCl to give H plus and Cl minus doesn't appear in the rate equation. Do you understand? Only you will consider.
But the concentration of HCl defines the concentration of H plus,
that is
right?
fine, but that will not appear in the rate equation. assuming that HCl is highly acidic and instantaneously giving the H plus. Okay, so it is more prevalent for weak acid. Okay, so in specific acid, we will consider only the H plus. From where it is the H plus is coming, okay, suppose H plus, so HCl will not have much effect on H plus. Do you understand my point? If it is the acetic acid, then it will have an effect. So specific acid is telling that we will deal only with the H plus. Okay. So what is the source of H plus or any other acid which is giving the H plus, that will not appear in the rate determining step. That is the reason whenever you will do a specific acid catalyst reactions, you need to add strong acid so that it can easily ionize to give the H plus, not weak acid. That is coming for the general acid catalysis. Does it make sense or not? If it's not, I will repeat. So in specific acid catalyzed reactions, you only care about the H plus. Okay.
Okay, sir.
So you need to add such a acid that it will instantaneously giving a H plus ion in the water. It's like strong acids, not acidic acid.
Sir?
Yeah.
How do we arrive at that plot in the next slide?
Which one?
Yes, this log K observed versus
Yeah.
pH. I mean, we should get a linear equation, right, with negative slope.
Yeah, you need to derive it. You need to derive it. Okay. So in experiments, what you will do? K of, suppose you will do a multiple experiment. Suppose you will do 4 experiments. Okay.
Yes, sir.
Hello. Yeah, you will do 4 experiments. Suppose you are keeping the substrate concentration same. Substrate concentration same, but varying amount of H plus.
Okay, sir.
Makes sense. It's a very simple way I'm telling you. So you will make a 4 stock solutions. Okay, same substrate concentration, but with various pH, so that your concentration of H plus is different.
But sir, how does K observed depend on H plus? I mean, this is a constant, right? This should not
Yeah,
change.
yeah.
That must depend on H plus. That's okay, but how does K observed depend on H plus?
Why not K objects will depend on H plus? Because, okay, look, so because your rate will change. Your rate is,
Because capital K also depends on H plus.
yeah. So your rate is dependent on the K into H plus for both. Okay. So your rate constant K ops will change because your rate is changing because of the changes of a concentration H plus. Do you understand?
No, sir.
Yeah, and someone also told this is correct. Okay, so your K ops, this is K, this one is also dependent on the capital H plus. Yeah, this one. So equilibrium will also shift with the concentration of H plus, right?
But sir, H plus is, I mean, H plus is a catalyst. It should not affect the equilibrium.
Why not? It also dependent on the catalyst concentrations also.
But
if it is the first order with respect to H plus, okay, then rate will increase on increasing the concentration of H plus catalyst. Any equation, whenever you will do, suppose you have a catalyst, suppose it is an enzyme plus substrate, it is giving product. Okay.
Yes, sir.
We will do the rate law. So what is the rate law? If it is first order with respect to substrate, okay, then rate will be equal to rate constant into catalyst. This is the enzyme catalyst, suppose, into substrate. Okay.
Yes, sir.
Okay. So your rate constant will also depend on, okay, how much is varying the specific acid catalyst, because your rate constant here is a KH plus is actually dependent on the K2 and K. So rate will increase on increasing the substrate concentrations. Rate will also increase on increasing the catalyst concentration because it is the first order. if it is first order. Okay, in specific acid catalyzed reactions, your rate K ops is constituted with K2 and K, capital K. Okay. You can see here this capital K is the equilibrium constant, which is the SH plus divided by concentration of S into H plus. Okay. So if catalyst concentration increases, then definitely equilibrium will sit on the right hand side.
But sir, in the final rate law, we have the equilibrium constant multiplied by the concentration of H plus, right? So the K, the capital K into H plus will remain constant if substrate is constant, right? It should not depend on the concentration of H plus.
This will depend.
So, but how? I mean, capital K into H plus will remain constant, right? It will be equal to SH plus concentration of.
Look. This is actually there are two component. The second rate constant into first rate constant. Do you understand my point? First rate constant, second rate constant. It is obvious that second rate constant is dependent on the concentration of H plus. Because this is the. Is it correct? Second rate constant is dependent on the concentration of H plus. Do you understand? So if you do that, then it will be dependent on the H plus. So rate constant K ops will also dependent on the pH. Do you understand my point? This will get it. And this will also not vary if you change the concentration of H or weak acid or little bit of acid base if you add it, keeping the pH same. Okay.
Okay, sir.
If it does not make sense, I will derive it, then I will send you. Okay, maybe next class tomorrow.
Yes.
Okay, specifically.
Sir,
Yeah.
Sir, I needed one clarification that this particular graph with m equal to -1 is for only those processes where H plus is directly available, and we are not considering the dissociation step.
No, that is the yellow highlighted part is meaning someone asked. Yeah.
Okay.
Yeah. Okay, that is the reason whenever you will do an experiment of specific acid catalysis, we will not consider from where H plus is coming. Okay, so assuming that H plus is available, so that we need to use the strong acid. So the strong acid we can assume that 100% is dissociated with giving H plus. Okay, it is freely available. Okay, it is not coming from weak acid. Those will come in the general acid catalyst reactions, whether H plus is not very free, and those CH or CH bond, okay, will be in the rate determining step. Here it is not a rate determining step. This is a fast process. Barrier is low. So which one is the rate determining step? Which has the higher barrier? Slow process. It cannot be a rate determining step because it's reversible. Back and forth. So it has a less barrier. Okay. So in specific acid catalyzed reaction, only H plus is a matter. From where H plus is coming, okay, what is the dissociation constant from HA to HA? We will not care about that. So only pH is the matter. Okay, normally, usually, whatever I showed, or suppose there is an example here in the ring opening reactions of epoxide in catalyzed by H plus. Okay, so the second step, okay, the rate determining step, slow step, is followed by the reversible protonation step. Okay. One of the important part I just want to tell that here you can see this is mentioned. I took it from book. Okay, the proton transfer is not involved in the rate determining step. So very important. Is it happening, the proton transfer? proton transfer is happening in the reversible step, not in the rate determining step. Okay. So if proton transfer occurred in the rate determining step, then what experiment you will do? If proton transfer occurred in the rate determining step, then what experiment you will do to understand to know that whether proton transfer is happening in the rate determining step or not?
So kinetic isotope.
Okay.
Kinetic isotope effect. Yeah, exactly. Exactly. Okay. Kinetic isotope effect. I'm coming next for general acid catalyst reactions. So everything is connected to the 4 experiments. Okay, whatever I told you. So suppose this is a specific acid catalyst reactions. What will be the activation parameters? Activation parameters for this reaction in the slow step. What should you expect the entropy of activation changes? Plus, negative, or 0? What will happen?
So negative.
Decreases.
This is
Negative.
Negative.
this is decreases, right? All right. What about here?
So here also negative.
What is also negative? What about here? These are the examples I gave you, right? I'm going back. What about here? Hello. What is this?
So here the migration takes place, right? In the RDS.
Yeah. So what do you expect? Del S will be positive, negative, or 0? Or
Can
maybe
it
Should be positive since
Positive.
the steric effect is
Very
steric
steric
interaction is reduced.
positive, but how much? It might be. You are correct.
Positive.
It might be little bit of positives. It might be, but not much. I would expect it is close to 0.
Yes.
Or maybe plus little bit. Okay, if it is plus 1, plus 2, it is not much meaningful. Maybe little positive, right? So depending on the examples, I'm telling you, okay, there are other examples are there. Okay. It all depends on, this is a simple unimolecular. That's why I'm going back to give the examples. Okay, the last example, that is a unimolecular reaction, right? There is a migration. Methyl groups is migrating, right? 1 to shift, right? But here this is the bimolecular. So it depending on the type of reactions, the specific acid catalyzed reactions, the rate determining step can be unimolecular or bimolecular. It all depends. If it is a bimolecular, then you should expect a negative entropy. If it is unimolecular, you may get positive or maybe 0. You are correct, right? You told that this is negative. First one maybe a little bit of positive, maybe, or maybe 0 because it is a unimolecular. So here the entropy of activation is meaningful or not for specific acid catalyzed reactions? Can it tell? Can it tell?
No, no, sir.
No, sir.
In general, no. In general, no. If you know, but in general, no. It may be positive, it may be negative, it may be 0. But if you are determining a very specific reactions, for example, here, and if you are getting the del S of activation is negative, then yeah, it will support. It is supporting here, right? If del S is negative, then it is supporting this rate determining step.
Sir,
Yeah.
I had one doubt.
Yeah.
Like here, although in MEOH is attacking the ring, but the ring is also opening. So like, won't del S would be somewhere close to 0 because both the things are happening. On one hand, we see crowding happening and ring is also opening. So ring opening kind of
That's a
nullify
very
the
good.
effect.
Okay, good. That's a very good question. I'm going to tell next. Okay, I miss the next. That is the reason I told you, right, that here, depending on the reactions, unimolecular reactions or bimolecular reactions, the entropy of activation is not much meaningful. Okay. If it is very specific, then it may indicate, for example, here, but simultaneously the ring opening, when it is a ring, this is quite strained, right? It's a strained system. Any kind of ring, suppose there is a NH or N. Okay. So when the ring opening is happening, then your entropy of activation is increasing, but simultaneously it's a bimolecular reaction, right? It is bimolecular reactions. You should expect that this will decrease the entropy. So that can neutralize. Either it can neutralize with 0 or it can be little bit of negative. It can be positive. You cannot predict. You cannot predict, right? You are correct.
Sir.
Yeah.
So by this logic which you just told,
Yeah.
then we cannot even predict the delta S positive for the
Cannot
delta
predict.
S of transition state for the SN2 mechanism also, because there
Why
also
not?
one bond simultaneously breaks and one bond simultaneously forms. I mean, we cannot even tell there. It's just like this specific acid catalysis reaction only, right?
Yeah.
So how do we account for that in SN2 reactions, that
Now
delta
look,
negative?
in SN2 type of reactions, okay, bond is breaking, but this is the transition state.
Okay.
Okay, this is a transition state.
But
So
this
you
is
need
happening
to,
here also, right?
yeah, this is a transition state. You need to look at from the ground state and in the excited state. Okay, so look, there is no strain, but here specifically for this kind of reactions, this is a strained molecule. Okay, this is the thermodynamics of this kind of molecule is purely coming from the strain of the ring, because you know that 6-member ring is very stable thermodynamically. 5-member ring is little less stable, but the cyclobutene or cyclopropene is highly strained molecule. Okay, so those kind of reactions, if you don't have the acid, still the reaction will happen in water, but it will be slow because the product is strainless. It is much more lower in energy compared to the starting material. But that is not the case for SN2 type of reaction. Okay, that is the reason I am telling here for specific acid catalyzed reactions, in all depends on the nature of the reactions. You cannot predict whether there will be positive or negative. Here will be negative. Okay, there is no strain, but here is a huge strain. Any kind of steric closed ring molecule other than 5-member or 6-member ring, okay, it is always try to open the ring because of the huge thermodynamically favorable of the opening of the ring opening product. Okay, is it clear? It is not the case, but here this is a very specific case. So for acid catalyzed reactions, depending on the type of the reaction, it is very hard to predict del S will be positive or negative. Okay, because I don't know which girl who asked. Okay, so this is quite thermodynamically favorable because it is opening the ring. This is a very specific case. But if it is a 6-member ring or 5-member ring, then ring opening, it will not give much thermodynamically or entropically favorable case. This is a restricted molecule, so entropy is very tight. That also, okay? Is it clear? So for specific acid catalysis reactions, del S is actually not much meaningful. It can be plus, it can be minus, it can be 0. It is hard to predict depending on the nature of the substrate as well as the reaction. So one of the reactions I gave you, the specific acid catalyst hydrolysis of ethyl acetate, another is the 1,2 shift, that is unimolecular reaction, and these are ring opening reactions. Okay, so the experiment you will do solely depending on the plot of log chaos versus pH, whether it is pH dependent or not. Is it clear? Any questions next? Okay, I'm very slow. 50 minutes is passed. Any other questions? Is it clear? Okay, who asked these questions? SN2 reactions.
So me.
Yeah, is it clear?
Sir, actually, I I'm still not able to understand that in SN2 reactions also in the transition
So
state.
SN2 reactions, your bond is also breaking. Okay. Suppose in SN2 reactions it is a methyl. Suppose it is a methyl bromide. You see Br bond is also breaking and getting elongated.
Okay.
Right. But simultaneously, your another bond is forming also.
Yes, sir.
Right. So if you look at from the ground state to the excited state, okay, so two molecules are coming close to each other, even though one bond is getting longer, but another bond is forming also.
Yes, sir.
Right. It is also increasing the steric crowding of the carbon center. So overall, your ground state has two molecules, the entropy. I understand your CBr bond, when it will be breaking or getting elongated, it will increase the entropy. Okay. But in the overall, you have two free molecules in the excited state. They are coming close to each other. Even though couple of bonds, it may get elongated. Okay. It may get elongated. It is elongating CBr bond, but simultaneously another bond is forming also. Suppose carbon oxygen bond is forming because it is transitioning from sp3 to sp. It is now carbon center is 5 membered. Five bond is forming. Right. It is a four bond versus 5 bond.
Sir, that is what I'm saying in this case also in the
but this case
opening.
You are correct. You are correct. So this case, two molecules are coming close to each other, and you will tell positive. That's why I told yes. Right. But this is a tricky case that I'm supposed to tell you. Okay. Before, but who's the girl here? She asked also. Okay. So in general, this is a positive. Is it? Sorry. Let me check.
Negative.
In general, this is the negative. In general, this is the negative. Two molecules are coming close to each other and giving the negative. Okay.
Yes.
In general, but experimentally, you may get positive also. It's a special case that I'm trying to say.
So it's all experimental, right? We cannot.
Experimental value is a very special case because this is the tricyclic ring opening systems. Okay, it's a very special case.
Yes, sir. Got it.
Understand? Okay. Otherwise, this is negative. I will close my eye and I will tell this is the negative because two molecules are coming close to each other in the transition state. Okay, and it is giving a unimolecular product. Okay, this is the negative. This is a huge negative. It will be the negative entropy, no doubt. But it's a very special case because when a ring is cyclobutene or
yes, sir. High angle strain.
Okay, so this also favor the thermodynamics also. This is a thermodynamic parameter. Okay, right?
Yes.
You understand my point? That is the thing. Is it clear or not?
Yes, sir.
Yeah, now it is clear. It's a very special case. It's a very specific case. Okay, but it's a very common. Okay, when the ring opening reaction, suppose it is a very, it is actually industrially used reaction. Okay, so why we are giving the examples? Okay, you are the chemical engineer. You will be chemical engineer, not yet, right? You will get the degree of chemical engineer because ring opening. Ring opening polymerizations is an industrial process. Okay, ring opening polymerization using the metathesis catalysis, people got Nobel Prize. Polylactides, this is the ring opening polymerization to give the polylactic plastic bags, the biodegradable plastic bags. Okay, those are happening by ring opening polymerizations. Okay, so ring opening systems is a very common starting material. Why? Because ring opening is thermodynamically favorable. It will favor, even if you add little bit of catalyst, it will be very fast because this is a closed system. Okay, so ring opening is a very thermodynamically favorable. Okay, because it will release the strain. Okay, this is one of the example.
Sir,
polylactide.
you had given 4 ways to tell like what kind of mechanism, like Hammett's plot. So you had given 4. So even suppose if I want to confirm that if Br2 is going through like if it's forming a ring or if it's attaching individually, can't I even use IR spectroscopy? Like if you see the vibrations, if it would be a ring transition state, then it would be highly strained and the value would be much different than if it's attaching individually, right? So why isn't that a method to determine the rate, determine the mechanism of reaction?
You can do that, but let me tell you one thing. Okay, you may think about that. I can use the instrument, right? Instrument, right?
Yes.
Instrument has some limitations. So why we are using this kinetics? This is all the kinetics, right? This is you will determine by kinetics, right? This you will determine by kinetics. Everything is by kinetics. Why will do kinetics? Okay, right? By titrations or something. Look, I told you that this, you want to investigate this step, right? This is the most key step. Am I correct?
Yes, in general, checking
I
this.
thought I will finish the general acetic catalyst mechanism. Then actually it will be more distinguished by 4 experiments. Okay, we will discuss tomorrow. Okay, so this is the experiment you are going to distinct by experiments. Okay. Look, what about the transition state? What is the lifetime of the transition state? What is the lifetime of the transition state?
Very small.
Very small. Okay. What is the time scale of IR? You just look at what is the time scale of NMR? 3 seconds. Okay.
Okay. Okay.
Understand? So if the time scale of an instrument is much longer than the lifetime of the rate determining step, then you cannot determine. That's why you need a femtosecond laser spectroscopy, not all cases, okay, to determine or to find the nature of the rate determining step or transition state, and people got Nobel Prize for that. Do you understand my point?
Yes, sir.
IR, NMR you can use to characterize this starting material or product. But it will be very difficult. What is the transition state, because it's very short lived. Okay, suppose IR it has a microsecond, but your lifetime of the transition state or rate determining step is femtosecond. Do you understand my point? So it is a similar kind of photo and movie. Why? What is movie? You are engineering people. What is movie? Movie is taken by a lot of frames of photos, right? And they're moving
Yes,
fast.
sir.
Am I correct? I don't know about movie. Am I correct?
Yes, sir.
Right. So our eye cannot sense the changes of photos. Am I correct or not?
Yes, sir.
That is a movie. Looks like it is a moving, right? And those are the photo. Am I correct or not? So if it is moving the photos very fast, right? Then it looks like a movie, because our eye cannot detect the fast movement of the photos. I think this is the best example I can ever give for this kind of example, right? Because our eye has a capacity to sense each and every photo. So we cannot distinguish that it is moving. Same thing here. Am I correct or not? Is it clear?
So we can add laser spectroscopy. Like it can be the 5th way in which we can see the mechanism. Why only 4? Like why are we limiting to?
But laser spectroscopy, there is a limited case. You cannot tell very specifically what is going on. There is a limited case. Okay, laser spectroscopy is you will put the laser and some property will be changing. Okay, that will not give the full picture of the rate determining step of a reaction.
Yes.
It's a specific case. What is laser spectroscopy? There's a physical things. Okay, you will put a laser and get the molecule will be excited, and then it will deactivated. Okay, and that is a different topic. That is called pulse pump laser spectroscopy. Okay, so that will not give the complete picture. I'm giving the complete picture, right? In SN1, SN2, what is going on, right? So laser spectroscopy cannot tell that, okay, methoxy is attacking here and it is leaving here. Do you understand my point?
Yes.
Any questions? Then I'll stop. It's 12 o'clock already. Oh, I am very slow. I think my Blackboard teaching is quite faster than the slide teaching. Actually, I'm supposed to be. I don't know how many classes left. Tomorrow, day after tomorrow. Next week we have class. This Saturday we have class. Still, I want to teach some material chemistry also. Okay, so tomorrow we will finish the GNL acid catalysis and base catalysis. Okay, and then whatever you have questions, I think you ask me at the end. Okay, so 50 minutes and then I am here half an hour. You ask me the questions. Okay, I am allowed to ask your questions, but thing is that it is taking time. Okay, at the end or any quick questions you just ask. Okay, because only specific acid catalysis you took one class. Okay, so that is the thing. Okay, anything else? If it's not, then I will see you tomorrow. Okay, so we'll discuss whatever the questions. Okay, maybe I will come 10 minutes before tomorrow. Okay, at my 10:50. So whatever questions you have, we will discuss, and then I will go for GNL acid catalysis and GNL acid and base, and then I will be another half an hour to ask all of your questions. Okay. All right. So see you tomorrow. Bye bye.
Sir, we have a class tomorrow.
Thank you, sir.
What happened?
Sir, do we have a class tomorrow? Sorry, I'm confused, but.
Oh, sorry, Wednesday. Wednesday.
Okay.
Thursday. Day after tomorrow. Yeah. I don't know, Saturday do we have class or not? We should have a class because last week we missed for the Diwali. So anyway, okay. So see you day after tomorrow.
Thank you, sir.
Thank you.